Picture this: a river so old, its waters have carved through time itself, flowing uninterrupted for hundreds of millions of years. This isn't just any river. It's the world's oldest, a living relic from an era before the first dinosaurs even walked the earth. Its currents whisper secrets of a planet still taking shape, of continents cracking apart and colliding, of life itself crawling onto land for the very first time. Today, we're stepping onto its ancient banks to uncover what this timeless waterway can reveal about the dawn of our world. Think about the oldest thing you've ever touched: a fossil, maybe, or a piece of ancient pottery. Now imagine something infinitely older, a river that has witnessed the birth of mountains and the slow dance of tectonic plates. Its sediments are like pages in a geological diary, recording everything from the chemistry of Earth's earliest oceans to the moment plants first took root on dry land. This river isn't just a body of water, it's a time machine, and we're about to dive deep into its currents to piece together a story older than humanity itself. What makes this river so extraordinary isn't just its age, but the mysteries it holds. How did land first emerge from the primordial oceans? What forces sculpted the earliest continents? And what role did rivers like this one play in shaping the world we know today? The answers are hidden in its rocks, its fossils, even the very path it cuts across the landscape. By the end of this journey, you'll see Earth's history in a whole new light, because this river doesn't just tell us about the past. It helps us understand the fragile, ever-changing planet we call home. So let's begin where the story does, at the water's edge where time flows backward and the secrets of the world's infancy wait to be uncovered. Deep in the heart of Australia, where the red desert stretches endlessly under a blazing sun, flows a river that defies time, the Fink River. Scientists believe its waters have carved through this landscape for more than 350 million years, making it not just old, but the oldest known river on Earth. To put that into perspective, when the Fink first began winding across the continent, the landmasses we know today were still part of the supercontinent Pangea, and life on Earth was just beginning to venture onto dry ground. What makes the Fink so special isn't just its age, but its resilience. This river has survived the rise and fall of mountain ranges, the slow drift of continents, and countless cycles of erosion. While other rivers have vanished or changed course dramatically over the eons, the Fink has stubbornly held its path, offering geologists a rare, unbroken record of our planet's transformation. By studying the layers of sediment it has deposited and the ancient rocks it has exposed, scientists can piece together how landscapes evolved, how climates shifted, and even how early rivers shaped the land for the first plants and animals to colonize. Dating a river this old isn't as simple as reading a calendar. Researchers use a combination of techniques, from analyzing the minerals in its sediments to mapping the surrounding geology for clues about its origins. The Fink's course cuts through some of the most ancient rock formations on Earth, revealing layers that tell stories of vanished seas, volcanic eruptions, and the slow but unstoppable forces of erosion. These clues help scientists reconstruct not just the river's history, but the broader saga of how Earth's surface became what we see today. This river isn't just a relic, it's a living laboratory. The way it interacts with its environment today mirrors processes that shaped continents hundreds of millions of years ago. By understanding how the Fink has persisted through unimaginable spans of time, we gain insights into the fundamental forces that built our world. And as we follow its winding path, we're not just tracing the history of a single river, we're uncovering the story of how land itself came to be. Rivers like the Fink don't just flow, they remember. Every twist of their course, every layer of sediment they deposit, is a snapshot of Earth's past preserved with astonishing clarity. Think of them as nature's own history books, with chapters written not in ink, but in stone, sand, and fossilized clues. The Fink's bed, for instance, contains ripple marks frozen in time, left behind by currents that flowed over 300 million years ago. These delicate patterns, perfectly preserved, tell us the river once ran shallower or faster than it does today, offering a glimpse into climates and landscapes long vanished. But rivers don't just record local changes, they capture global events. Volcanic eruptions thousands of miles away left ash layers in the Fink's sediments, like time-stamped pages in its geological diary. Even the aftermath of asteroid impacts can be found here, with traces of rare minerals or shocked quartz grains hinting at catastrophic events that reshaped the planet. These deposits are more than just curiosities, they're proof that rivers like the Fink are interconnected with Earth's grandest dramas, silently archiving everything from quiet shifts in rainfall to planet-altering disasters. Perhaps most astonishing is how rivers preserve evidence of life itself. In the Fink's ancient banks, scientists have found fossilized fragments of early plants, their cellular structures still visible under a microscope. These fragile remnants survived because the river's steady deposition buried them quickly, protecting them from decay. For researchers, these fossils are like opening a time capsule from the moment life first crept onto land, revealing how plants adapted to survive in a world where dry ground was still a new frontier. The concept of river memory goes beyond just storing old rocks. It's about how waterways retain the echoes of their own past. The Fink's winding path, for example, follows grooves carved during much wetter periods, its modern flow still tracing routes established when the climate was radically different. Even when rivers seem to change, their underlying blueprint often stays the same, a testament to the enduring power of water to shape and remember the land. By reading these clues, we're not just studying a river, we're deciphering the autobiography of the Earth itself, written in currents and stone. Long before towering mountain ranges or sprawling forests existed, Earth was a world of fire and water, a place where the first land struggled to emerge from a global ocean. Scientists now believe rivers like the Fink were the architects of that transformation, carving the earliest continents into existence one drop at a time. Picture a newborn Earth, its surface still steaming from volcanic eruptions, with thin patches of crust cooling into brittle rock. When rain fell on this fragile landscape, it didn't just pool, it sliced through the weakened stone, etching the planet's first river valleys into the rock. These weren't gentle streams, but torrents of water fueled by relentless storms, their currents gnawing at the land and carrying away debris grain by grain. This wasn't just erosion, it was creation. As those early rivers dumped their sediment into shallow seas, they built deltas that would eventually rise above the waves. Over millions of years, this cycle of cutting and depositing stacked layers of sand and mud into thick blankets, compressing under their own weight until they hardened into new land. The Fink's modern path offers a glimpse of this ancient process in action. Its winding course through Australia's interior follows fractures in the crust that may have formed when Earth's first continents were still assembling themselves, suggesting that even the oldest rivers inherit their routes from the planet's deepest wounds. What's truly remarkable is how these processes balance destruction with rebirth. As rivers like the Fink wore down mountains, they also delivered the raw materials to build new ones. Minerals eroded from one region became the fertile soil of another, setting the stage for life to take hold. Fossil evidence suggests that the first plants to colonize land did so along these ancient waterways, their roots stabilizing sediment and accelerating the growth of stable coastlines. In this way, rivers didn't just shape the land, they helped it breathe, transforming barren rock into habitats where life could flourish. The Fink's endurance offers a rare window into this pivotal chapter of Earth's history. Unlike younger rivers reshaped by ice ages or shifting tectonic plates, its course has remained largely undisturbed, preserving a record of how water and rock conspired to build the world we know. By studying its sediments and the way it interacts with the surrounding landscape, geologists can trace a direct line back to the moment land first wrested itself from the sea, a slow, messy birth witnessed only by the rivers that made it possible. And as we stand on its banks today, we're not just observing a relic, we're seeing the blueprint for how continents grow, change, and endure across the staggering expanse of geologic time. The Fink River doesn't just flow, it dances. Its winding, seemingly aimless path across the Australian outback isn't random. It's a choreography written by the movements of continents themselves. Every bend, every sudden turn mirrors collisions and ruptures that happened hundreds of millions of years ago, when the Earth's crust was a restless puzzle of shifting plates. To understand how, look closely at where the river abruptly changes direction, bending around what now appears as nothing more than low hills or dry plains. These aren't accidents of erosion, they're echoes of mountain ranges that once towered as high as the Himalayas, their roots still guiding the river's course long after the peaks themselves have crumbled to dust. Take the Alice Springs orogeny, a colossal tectonic event that folded and fractured Central Australia around 300 million years ago. The forces that buckled the land here were so immense, they left behind hidden scars in the crust, fault lines and fractures that still influence the Fink's path today. Where the river zigzags sharply, it's often tracing these ancient weaknesses in the earth, like a car following cracks in an old road. Even more astonishing, some stretches of the Fink run parallel to long-vanished mountain chains, their alignment so precise that geologists can reconstruct the orientation of ranges that haven't existed for ages. It's as if the river remembers the continents as they once were, refusing to forget the shapes they used to hold. But the Fink's story goes deeper than local geology. Its broader path across Australia aligns with the grander saga of supercontinents, specifically Pangea, the last time all Earth's landmasses were joined. When Pangea began breaking apart around 200 million years ago, the stresses tore at Australia's interior, creating zones where the crust was stretched thin or shoved upward. The Fink, already ancient by then, adapted to these changes, its waters finding new routes through the fractured landscape. Today, scientists can read these adaptations like a diary, using the river's course to map not just how Australia evolved, but how the planet's landmasses have rearranged themselves over incomprehensible spans of time. What's revolutionary about this idea is that rivers aren't just passive observers of tectonic shifts, they're active participants. As continents collide or rift apart, rivers respond by carving new valleys, abandoning old channels, or even reversing direction. The Fink's persistence makes it a rare witness to these changes, its path preserving a record of forces that would otherwise leave no visible trace. Younger rivers might erase this history, but the Fink's age means its memories are written in stone, layer upon layer. By studying its meanders alongside satellite data and seismic surveys, researchers can piece together how the Earth's crust behaved under pressures we can barely imagine, turning a single river's twists and turns into a global story of movement and transformation. This transforms how we see rivers not just as water flowing downhill, but as living archives of the planet's deepest rhythms. The Fink's bends are like wrinkles in time, each one marking a moment when the Earth reshaped itself. And if we know how to read them, they reveal secrets not just about the land's past, but about the forces still shaping it today. After all, the the same tectonic processes that guided the Fink's birth are still at work, slowly rearranging continents beneath our feet. In that sense, the world's oldest river isn't just a relic. It's a reminder that the ground we think of as solid is always imperceptibly on the move. Beneath the Fink's shimmering surface lies a hidden library, layer upon layer of sand, gravel, and clay stacked like the pages of an ancient book. These sediments aren't just debris, they're Earth's autobiography, meticulously recording every chapter of the planet's history. Each grain tells a story, whether it's volcanic ash from an eruption older than the dinosaurs or a fleck of gold washed down from mountains that vanished eons ago. To read these layers is to travel backward through time, uncovering landscapes lost to the ages. One of the most powerful tools for decoding this archive is isotopic dating, a technique that measures the decay of radioactive elements trapped within minerals. Take zircon crystals, for instance, tiny time capsules found in the Fink sediments. Some of these zircons date back over 4 billion years, making them older than nearly every rock on Earth's surface. By analyzing the uranium and lead atoms inside them, scientists can pinpoint their age with astonishing precision. But these crystals do more than mark time. They carry chemical signatures that reveal what the environment was like when they formed. Traces of oxygen or rare earth elements, for example, can indicate whether the zircons crystallized in water or molten rock, offering clues about the planet's earliest continents and oceans. The Fink sediments also preserve snapshots of vanished worlds. In one layer, you might find rounded quartz pebbles, evidence of a long-vanished beach where waves once lapped. In another, flecks of mica glint like forgotten stars, hinting at a time when the river flowed through lush, rain-soaked valleys instead of desert. Even the size of the grains speaks volumes. Coarse gravel suggests fast-flowing currents, while fine silt points to calm floodplains. Piecing together these clues lets geologists reconstruct entire ecosystems that flourished and faded millions of years before humans walked the Earth. Perhaps the most startling revelation comes from how these materials interact. When zircon crystals eroded from ancient mountains are found alongside plant fossils in the same sediment layer, it creates a bridge between geology and biology. Suddenly, we're not just studying rocks, we're seeing how rivers like the Fink transported the very minerals that nourished the first land plants, stitching together the story of how life and landscape co-evolved. The river's bed becomes a mosaic, each fragment a puzzle piece in the grander picture of Earth's transformation from a water world to the diverse continents we know today. What emerges from these layers isn't just a timeline, it's a living portrait of resilience. The same forces that carved the Fink's path also shaped the planet's destiny, turning barren rock into fertile ground and chaos into order. And as the river continues to write its story, grain by grain, it reminds us that the Earth is never truly still. Even the oldest landscapes are still being rewritten, one sediment at a time. Some of the most extraordinary pages in the Fink River's geological diary aren't written in stone at all. They're written in bone, leaf, and spore. Along its banks, scientists have uncovered fossils so delicate they seem impossible to survive the ages. The imprints of fish that swam when this desert was an inland sea, the ghostly outlines of leaves from plants that were among the first to conquer dry land. These aren't just remnants of life, they're snapshots of evolution itself, frozen in the river's mud at the precise moment Earth's story took a dramatic turn. Take the Devonian period, around 400 million years ago, when the Fink's waters teemed with armored fish unlike anything swimming today. Fossilized fragments of their bony plates and teeth tell us this wasn't just any river. It was a frontier where aquatic life was experimenting with traits that would eventually allow vertebrates to crawl onto land. Some of these fish had primitive lungs alongside gills, an evolutionary innovation that let them gulp air in oxygen-poor shallows. Others developed sturdy fins that could prop them up on muddy banks, foreshadowing the limbs of amphibians. The Fink didn't just witness this transition. Its seasonal floods likely created the perfect nurseries for these experiments, with shallow pools that dried out periodically, forcing creatures to adapt or perish. But the river's role in life's great leap wasn't limited to animals. In its silty deposits, paleontologists have found spores from the earliest vascular plants, humble pioneers like Cooksonia, which stood just a few centimeters tall but possessed a revolutionary feature: internal tubes to transport water. These fragile stems, preserved in astonishing detail, mark the moment plants evolved the machinery to thrive far from water's edge. What's remarkable is how the Fink's dynamics aided this revolution. Seasonal floods would have spread sediment rich in minerals across low-lying plains, building the first fertile soils. As plants took root, their decaying matter added organic richness, creating a feedback loop that turned barren rock into habitats where more complex life could flourish. The river didn't just passively record these changes, it actively shaped them. Meandering channels created oxbow lakes and backwaters that became biodiversity hotspots, offering sheltered environments where new forms could evolve. When floods receded, they left behind networks of temporary ponds, each one a laboratory for adaptation. Even the chemistry of the water played a role. Minerals like phosphorus, eroded from upstream rocks and concentrated in floodplains, became the building blocks for bones and cell membranes. In this way, the Fink wasn't just a backdrop for life's terrestrial debut. It was a collaborator, providing both the stage and the materials for Earth's most audacious evolutionary experiments. Today, these fossils do more than satisfy scientific curiosity. They rewrite our understanding of rivers as engines of biological innovation. Every spore, every fish scale whispers the same truth, that the conquest of land wasn't a solo endeavor, but a partnership between life and the waterways that nurtured it. As we sift through the Fink's ancient mud, we're not just uncovering fossils, we're reading the blueprint for how life, against all odds, transformed a rocky planet into a living world. The Fink River's rocks don't just hold fossils, they hold weather reports from deep time. Hidden within its layers are clues to climates so alien, they'd seem like science fiction if not for the physical evidence. Imagine a time when Central Australia wasn't a desert, but a lush wetland crisscrossed by rivers swollen with monsoon rains, or an era when the entire region lay buried under glaciers, its silence broken only by the groan of moving ice. These aren't guesses, they're stories pulled directly from the river's sedimentary archives, written in the language of chemistry and stone. One of the most powerful tools for reading these ancient climates lies in oxygen isotopes, tiny variations in the chemical fingerprints of minerals like calcite or quartz. When rainwater seeps into the ground and forms these minerals, it locks in the isotopic ratio of that moment's precipitation. By analyzing these ratios in the Fink's oldest deposits, scientists can reconstruct rainfall patterns with startling precision. Heavy oxygen isotopes, for instance, often signal hot, arid periods when evaporation was intense, while lighter isotopes point to cooler, wetter epochs. It's like finding a prehistoric rain gauge buried in the riverbank, still measuring storms that fell hundreds of millions of years ago. But oxygen isn't the only messenger from the past. Layers of iron-rich sediment hint at periods when the atmosphere held far less oxygen than today, causing iron to dissolve in water and settle in thick bands. Sudden shifts to red-colored strata might mark the arrival of dry, oxidizing conditions, while dark, carbon-rich layers could mean back-to-back floods drowned plants before they could decay. Even the shapes of sand grains, telltale's angular fragments suggest violent storms carried them short distances, while smooth, rounded ones imply long journeys in gentler currents. Together, these proxies paint a portrait of a planet in constant flux, where climates changed not over centuries but over millennia. What's revolutionary is how these ancient patterns align or clash with modern climate models. When researchers compare the Fink's paleo data with projections for future warming, eerie parallels emerge. Periods of abrupt climate shift in the geologic record often coincided with spikes in greenhouse gases, mirroring today's rising carbon dioxide levels. But the river's rocks also hold surprises, evidence that some regions stayed wetter than expected during past warm periods, challenging assumptions about how deserts respond to global change. These discrepancies aren't failures, they're opportunities to refine our understanding of Earth's complex climate machinery. This isn't just academic detective work, it's a survival guide. By studying how the Fink's ecosystem adapted to droughts or deluges in the past, we gain insights into how modern rivers might behave as the planet warms. Will arid regions like Australia's interior become even drier, or could shifting wind patterns bring unexpected rains? The answers matter for everything from agriculture to water conservation, and they're hidden in the river's strata. In a world facing climate uncertainty, the Fink's greatest gift isn't its age, it's its memory, offering lessons from a time when the planet faced changes even more dramatic than those we see today. The rocks are speaking, we just need to listen. The Fink River doesn't just endure the desert, it masters it. While most waterways in Australia's bone-dry interior vanish under the sun, reduced to cracked clay and dust, the Fink defies the odds. Its secret, a survival strategy refined over hundreds of millions of years. Unlike perennial rivers fed by steady rains or melting snow, the Fink is ephemeral, flowing only after rare downpours. But don't mistake its silence for surrender. Beneath the surface, its waters persist, trickling through hidden channels of porous sandstone, a subterranean lifeline that keeps the river alive even when its bed lies parched and empty. This isn't just resilience, it's ingenuity. The Fink's ability to go underground during droughts mirrors tactics seen in other ancient rivers, from the Mojave's buried Amargosa to Namibia's Kuwaisib, which carved canyons in the Namib Desert only to retreat beneath the sands. What unites these waterways is their geologic wisdom. They've learned to adapt to Earth's mood swings, storing water in secret reservoirs or shifting their courses to follow fractures in the crust. The Fink's intermittent flow isn't a flaw, it's a feature, a way to conserve energy until the next life-giving flood. The river's survival is etched into the land itself. After a rain, water rushes down its channels with startling force, scouring the bedrock and carrying nutrient-rich sediment to distant plains. These floods are brief but transformative, triggering explosions of life as dormant seeds sprout and aquatic eggs hatch in transient pools. Then, as quickly as it arrived, the water retreats, but not entirely. Some seeps into vast aquifers where it's protected from evaporation, slowly released through springs that sustain pockets of greenery in an otherwise barren landscape. This rhythm, flood and retreat, abundance and scarcity, has played out for eons, shaping not just the river but the ecosystems that depend on it. Yet the Fink story isn't unique. Across the globe, other fossil rivers whisper of similar adaptability, though many lost the fight. In the Sahara, radar has revealed the ghosts of waterways that once rivaled the Nile, now buried under dunes. Satellite images expose the skeletons of ancient deltas in Saudi Arabia's empty quarter, their branching veins visible only from space. These vanished rivers didn't fail. They were outmatched by climates that shifted too far, too fast. Their dry beds serve as cautionary tales and stark contrasts to the Fink's enduring pulse. What sets the Fink apart is its balance of persistence and flexibility. Its course has bent but never broken, adjusting to ice ages and supercontinents without disappearing entirely. That tenacity offers a lesson for our own era of climate upheaval. As modern rivers dwindle under dams and droughts, the Fink's ancient playbook storing water underground, embracing intermittent flows, and leveraging geologic resilience might hold clues for sustaining freshwater systems in an uncertain future. After all, this river has weathered changes far more extreme than anything humans have unleashed. Its survival isn't just a quirk of nature, it's a masterclass in endurance, written in water and stone. For the Arrant people, the Fink River isn't just a waterway, it's a living ancestor woven into their creation stories since time immemorial. Their oral traditions describe the river's birth in vivid detail, not as a geologic accident, but as the deliberate work of ancestral beings who shaped the land with purpose. One story tells of two giant caterpillars, the Yeperanai, whose bodies carved the river's winding path as they journeyed across the desert. Another speaks of the rainbow serpent, a powerful creator spirit whose movements forged valleys and left water in its wake. These aren't just myths, they're intricate maps of knowledge, encoding observations passed down through hundreds of generations. What's astonishing is how closely these traditions align with scientific understanding. The Arrant's description of the river's shifting channels, for example, mirrors modern studies of how the Fink's course has meandered over millennia. Elders speak of ancient floods that reshaped the landscape, events later confirmed by sediment layers showing catastrophic deluges. Even the timing matches, oral histories referencing times when the desert was green correlate with paleoclimate data revealing wetter epochs. This isn't coincidence, it's the result of deep observation where generations tracked subtle changes in water flow, vegetation, and animal behavior, compiling a living database of environmental shifts. The Arrant's connection to the river goes beyond physical observation. Their ceremonies and songlines, spiritual pathways traced through the landscape, often follow the Fink's course, marking sacred sites where water emerges unpredictably from the desert. These locations frequently overlap with geologic fault lines or underground springs, suggesting an intimate understanding of the river's hidden hydrology long before modern tools could map it. When elders describe sensing water beneath their feet or predicting floods based on bird behavior, they're drawing on knowledge systems refined over 60,000 years, offering insights science is only beginning to quantify. This fusion of indigenous wisdom and modern research is rewriting how we study ancient landscapes. Geologists now consult Arrant elders to locate sediment deposits or interpret erosion patterns, recognizing their narratives as time-tested field guides. In one striking example, traditional stories about rivers in the sky led scientists to discover fossilized river systems aligned with the Fink's ancestral path, buried under later rock layers. The collaboration reveals a powerful truth that science and indigenous knowledge aren't opposing forces, but complementary lenses for understanding Earth's history. The Fink's enduring presence has made it a bridge between worlds, between the measurable and the spiritual, the ancient and the evolving. For the Arrant, its waters are a thread connecting past, present, and future, a reminder that landscapes hold memory not just in rocks but in stories. As climate change reshapes the river once more, this blend of traditions offers more than just knowledge. It provides a model for resilience, showing how diverse ways of seeing can help navigate an uncertain future. The world's oldest river didn't just shape the land, it taught humanity how to listen. The Fink River's ancient flow invites us to wonder what makes one river survive hundreds of millions of years while others vanish without a trace. To answer that, we need to travel beyond Australia to places like the Appalachian Mountains of North America, where the New River carves its own path through time. Officially recognized as the oldest river in the United States, the New's origins stretch back over 300 million years, a contemporary of the Fink. But there's a stark difference. While the Fink winds freely across a desert, the New is trapped in a geological paradox. Its waters slice through mountains that didn't exist when the river first formed, a testament to its stubborn refusal to abandon its original course even as the land around it rose skyward. This contrast reveals a key factor in a river's longevity: tectonic stability. The Fink flows across the Australian Craton, a thick, rigid slab of Earth's crust that's remained largely undisturbed for eons. Like a steady table beneath a spinning top, this stability allowed the river to maintain its path with minimal interruption. The New River, however, had to contend with the birth of the Appalachians, a mountain-building event so violent it should have obliterated any existing waterways. That it didn't speaks to the river's ability to cut downward faster than the land could rise, etching its channel deeper as peaks grew around it. Yet this very struggle left the New vulnerable. Today, its flow is fragmented by dams, its ancient rhythm disrupted in ways the remote Fink has never experienced. Then there's Europe's Meuse River, another elder statesman of hydrology. Originating in France and flowing through Belgium and the Netherlands, the Meuse has witnessed the rise and fall of entire ice sheets. Its secret: adaptability. Unlike the Fink's near-static path, the Meuse has shifted its course repeatedly, skirting glacial advances and rerouting around sinking deltas. This flexibility kept it alive, but at a cost. Its sediments are a palimpsest of overwritten histories, making it far harder to read than the Fink's uninterrupted record. What the Meuse gained in resilience, it lost in geological clarity. The real outlier, though, is South Africa's Orange River, which drains a basin nearly 2 billion years old. While not as ancient in its current form, its headwaters tap into rocks that were part of Earth's first supercontinents. Yet the Orange's story is one of reinvention. Its modern course was shaped by relatively recent uplifts, erasing much of its deeper past. This highlights another truth. Age isn't just about how long a river has existed, but how much of its original identity remains. By that measure, the Fink stands alone, a river that has preserved not just its water, but its memory. What these comparisons teach us is that rivers, like civilizations, thrive under specific conditions. Tectonic calm helps, but so does the right balance of erosion and deposition, of change and constancy. The Fink's desert setting, ironically, became its salvation, sparing it the glacial rearrangements that rewrote Europe's waterways or the human interventions that tamed North America's. Its isolation preserved its purity, turning it into a time capsule of planetary history. This reshapes how we perceive geological time. Most ancient landmarks, mountains, canyons, even continents are ephemeral on Earth's timescale, endlessly recycled by plate tectonics. But rivers like the Fink offer continuity, a thread connecting us directly to the planet's infancy. Their persistence challenges the very definition of permanence, proving that even in a world of constant flux, some things endure by learning to flow with the changes rather than resisting them. Standing by the Fink today, we're not just looking at water, we're seeing time itself, liquid and unbroken, a current that has outlasted empires of rock and ice. Long before animals crawled onto land or plants took root, rivers like the Fink were quietly engineering one of Earth's most dramatic transformations, the very air we breathe. 2.5 billion years ago, our planet's atmosphere was a toxic cocktail of methane and carbon dioxide, barely recognizable to us today. Then came the Great Oxidation Event, a planetary upheaval where oxygen levels surged, paving the way for complex life. For decades, scientists focused on the role of oceans and cyanobacteria in this revolution. But new research suggests ancient rivers were unsung heroes in this story, acting as conveyor belts for the nutrients that made it all possible. The key lies in phosphorus, a humble element with world-changing power. As the Fink's ancestral waters eroded rocks, they unlocked phosphorus trapped in minerals like apatite, carrying it downstream to coastal seas. There, it became fertilizer for cyanobacteria, microscopic pioneers capable of photosynthesis. These tiny organisms thrived, releasing oxygen as a byproduct, but they needed a constant supply of nutrients to sustain their growth. That's where rivers came in. Studies of ancient sedimentary rocks reveal that phosphorus-rich river sediments spiked just before atmospheric oxygen levels rose, suggesting a direct link between inland erosion and oceanic oxygen factories. But rivers didn't just deliver nutrients, they transformed them. The Fink's modern chemistry offers clues. Its waters interact with iron-rich rocks, creating compounds that bind phosphorus in forms cyanobacteria can easily absorb. Similar processes likely occurred in primordial rivers, turning inert minerals into bioavailable fuel. This wasn't a one-time event, it was a feedback loop. As cyanobacteria flourished, they produced more oxygen, which reacted with land rocks to release even more phosphorus, accelerating the cycle. Rivers became the circulatory system of this planetary metabolism, connecting land and sea in a dance of chemistry and life. The implications are staggering. Without rivers to shuttle these nutrients, the Great Oxidation Event might have stalled, leaving Earth's atmosphere stagnant and lifeless. Even the timing makes sense. The event coincided with the rise of stable continents, when rivers could establish enduring networks to transport materials across vast distances. The Fink's endurance hints at why. Its persistence over eons allowed it to continuously weather rocks, ensuring a steady supply of life-giving elements to the oceans. This reframes rivers as more than landscape sculptors. They were atmospheric engineers. Their currents didn't just carve valleys, they helped tilt Earth's chemistry toward habitability, setting the stage for everything from jellyfish to dinosaurs to humans. And as the Fink flows today, its waters still carry traces of that ancient partnership, a reminder that the air in our lungs owes its existence, in part, to the quiet work of rivers billions of years in the making. Imagine a world without continents, just scattered islands of cooling lava poking above a global ocean, under a sky choked with volcanic fumes. This was Earth over 4 billion years ago, a place so alien that even the concept of a river seems impossible. Yet scientists now believe waterways existed even then. Not the meandering giants we know today, but strange, short-lived proto-rivers carving channels through crust so fresh, it was still warm to the touch. These weren't rivers as we understand them, but more like temporary scars left by runoff from torrential rains, their courses rewritten with every new volcanic eruption. The rocks that could confirm their existence have mostly vanished, recycled into the planet's churning mantle, leaving behind only whispers in the chemistry of ancient zircon crystals. The Fink's deepest ancestors might have been part of this primordial network. Geochemical clues suggest Australia's crust contains fragments of rock that survived from Earth's infancy, meaning the Fink's watershed could overlap with terrain that once hosted these proto-rivers. Picture a landscape where water didn't flow downhill so much as seep through fractured lava plains, its paths dictated by cracks from cooling rock rather than mountain slopes. These waterways wouldn't have lasted long, perhaps decades, before being buried under fresh eruptions, but each brief flow contributed to a slow, planet-wide process, leaching minerals from rock and ferrying them to the sea, a crucial step in making Earth habitable. Studying these phantom rivers is like trying to reconstruct a soap bubble from its shadow. The oldest intact sedimentary rocks, the usual record keepers of river history, date back only 3.8 billion years, leaving a half-billion-year gap in the geologic record. What little evidence exists comes from indirect sources, like isotopic ratios in ancient zircons that hint at interactions with liquid water. Some models suggest early rivers were fed not by rain, but by condensation from steam-rich volcanic plumes, creating acidic flows that dissolved rock at unprecedented rates. Others propose they were seasonal, appearing only during intense bouts of bombardment by icy comets. The Fink's endurance offers a rare window into this mystery. Its ability to persist across supercontinent cycles suggests it taps into geologic stability deeper than most rivers, a stability that might echo the behavior of those first proto-rivers. For instance, the Fink's modern path follows fractures in the crust that could be ancient beyond measure, weaknesses dating back to when Earth's crust was thin and brittle. Even its intermittent flow mirrors theorized patterns of early rivers, which may have alternated between flash floods and complete dryness as the young planet's climate lurched between extremes. What's revolutionary is how this reshapes our view of Earth's water cycle. Rather than waiting for continents to form, rivers might have been active players in creating them, their flows concentrating minerals in specific zones where thicker crust could accumulate. The Fink's stubborn refusal to disappear despite Australia's punishing climate hints at a deeper truth, that rivers aren't just products of geology, they're architects of it, with a legacy stretching back to the very dawn of land itself. Unlocking the Fink River's deepest secrets requires more than just shovels and hammers. It demands cutting-edge tools that act like time machines, peeling back layers of history without disturbing a single grain of sand. Take LiDAR, for instance. This laser-based technology fires pulses of light from aircraft, mapping the river's terrain with such precision that it reveals subtle ridges and depressions invisible to the naked eye. In 2019, a LiDAR survey uncovered a network of abandoned channels winding beneath the desert like ghostly echoes of the Fink's past courses. These ancient pathways, some dating back tens of millions of years, show how the river pirouetted around long-vanished obstacles, its bends preserving a dance of water and rock frozen in time. But to see beneath the surface, scientists turn to something even more powerful: satellite radar. By measuring how microwaves bounce off the Fink's floodplain, satellites like Sentinel-1 can detect changes in ground moisture or spot sediment layers buried dozens of meters deep. One breakthrough came when researchers noticed strange circular patterns in the radar data. Turns out, they were tracing the outlines of prehistoric oxbow lakes, dried-up loops the river abandoned as it shifted course. These long-lost waterholes, now invisible above ground, were once oases for megafauna like diprotodons, giant wombats that roamed Australia during the last ice age. Then there's the brute force approach: deep core drilling. Using rigs that extract pencil-thin cylinders of sediment, geologists have pulled up cores spanning nearly the river's entire history. Each layer is a time capsule. One might hold pollen from extinct rainforests, while another contains volcanic ash from an eruption older than the dinosaurs. Drilling near the Fink's headwaters in 2022, a team hit a layer of jagged quartz grains unlike anything around them. These turned out to be remnants of a meteorite impact over 300 million years ago, carried downstream by floods that washed debris from a crater now erased by erosion. Fieldwork here isn't for the faint of heart. Scientists like Dr. Sarah Jennings, who's mapped the Fink stratigraphy for 15 years, describe weeks spent in 120-degree heat, watching for flash floods that can erase a campsite in minutes. Her team once lost a drilling rig to a sudden sandstorm, only to find it half buried a mile downstream. Yet these hardships pay off in moments of revelation, like discovering a layer of microscopic plant spores so well preserved. Their cellular structures show how early vegetation stabilized riverbanks, preventing erosion and literally shaping the landscape. What's emerging is a toolkit as dynamic as the river itself. Drones equipped with thermal cameras track how water seeps through dry riverbeds at night, while ground-penetrating radar unveils fault lines that still guide the Fink's path. Even humble magnetometers play a role, detecting iron-rich minerals that hint at vanished waterfalls or rapids. Together, these technologies transform the river from a static landmark into a living archive, its every curve and grain whispering secrets to those who know how to listen. And as we'll see next, those whispers are leading to discoveries that rewrite textbooks. One of the most jaw-dropping discoveries along the Fink River came when geologists sifted through what looked like ordinary gravel, only to realize they were holding stones worn smooth by currents that flowed over 300 million years ago. These ancient pebbles, found near the river's headwaters, bear telltale marks of being rolled and rounded by water, their surfaces polished to a glassy sheen by millennia of relentless motion. But what's revolutionary isn't just their age, it's what they reveal about the supercontinent Gondwana. When researchers matched the mineral composition of these gravels to distant mountain ranges now separated by oceans, it proved that the Fink's ancestors once connected landmasses that later drifted thousands of miles apart. Then there's the mystery of the megafloods. In 2018, a team led by Dr. Liam Carter from the University of Adelaide uncovered sediment layers containing house-sized boulders stacked like toys in the desert, a clear sign of catastrophic flooding. By analyzing the size and distribution of these rocks, they calculated flows 10 times more powerful than anything the Fink experiences today. The kicker: these floods coincided with the breakup of Gondwana around 180 million years ago, suggesting tectonic upheavals didn't just crack continents. They unleashed biblical-scale deluges that reshaped entire river systems overnight. Dr. Carter's fieldwork paints a vivid picture. Imagine waterfalls taller than Niagara cascading over freshly split cliffs, carrying enough debris to bury cities. The Fink didn't just witness continental divorce, it recorded the violence in its sediments. His team's findings upended assumptions about how quickly landscapes can change, proving that rivers don't always evolve gradually. Sometimes Earth rewrites their stories in a single, catastrophic chapter. The river's sediments have also rewritten the timeline of Australia's desertification. Fossilized pollen grains preserved in the Fink's mud reveal that just 50 million years ago, this was a land of towering rainforests and crocodile-filled swamps. But drill deeper, and the record shows a dramatic shift, layers of gypsum and salt marking the onset of aridity, as Australia drifted northward into drier latitudes. This transition wasn't smooth. It pulsed between wet and dry periods, with the Fink alternately swelling into a mighty waterway and retreating to a trickle. For climatologists, these cycles are a warning proof that continental drift can flip ecosystems from lush to barren over geologic timescales. What excites scientists most isn't just what the Fink has revealed about the past, but what it promises for future discoveries. Its untouched strata could hold clues to everything from undiscovered mineral deposits to new insights about early life. As Dr. Priya Mehta, a geobiologist studying the river's microbial fossils, puts it, we've barely scratched the surface. The Fink is like a library where we've only read the table of contents. Every layer we peel back exposes new questions. The river's enduring flow ensures it will keep challenging our assumptions. Just last year, satellite data revealed underground tributaries no one knew existed, hinting at a hidden network that could rewrite maps of Australia's groundwater. Meanwhile, plans are underway to core even deeper into the riverbed, reaching sediments that might predate the first land plants. Each new finding confirms that the Fink isn't just a relic, it's a living archive, still writing Earth's story one grain of sand at a time. The Fink River's ancient currents don't just tell Earth's story, they whisper secrets about worlds far beyond our own. When NASA's Perseverance rover rolled across the dusty plains of Mars' Jezero crater in 2021, scientists immediately recognized the landscape, a dried-up river delta, its branching channels eerily reminiscent of the Fink's own floodplains. The parallels are uncanny. Satellite images reveal Martian valleys with the same sinuous curves as the Fink's meanders, their slopes etched by water that flowed billions of years ago. Even the pebble formations scattered across Mars' surface mirror those found along the Fink's banks rounded by flowing water, then left stranded as the climate changed. These aren't just coincidences, they're clues that rivers, whether on Earth or Mars, follow universal rules of physics and geology, leaving behind nearly identical signatures in the rock. What makes this connection groundbreaking is how it reframes our search for extraterrestrial life. The Fink's fossil record proves that rivers aren't just conduits for water, they're highways for nutrients, concentrating minerals like phosphorus and nitrogen in ways that could have jump-started biology anywhere. On Mars, where the now-defunct rivers once pooled into lakes like Jezero, these same mineral deposits might hold fossilized microbes or chemical traces of ancient metabolism. Scientists are already using lessons from the Fink to interpret Martian sediments, searching for layered rocks that could preserve organic molecules, just as Australia's ancient riverbeds protect Devonian fish spines and plant spores. The key insight: if life ever existed on Mars, its best chance of leaving evidence would be in the very places where water lingered longest: river deltas, floodplains, and underground channels, exactly like those the Fink has sculpted over eons. Mars isn't the only extraterrestrial classroom for river science. Saturn's moon Titan boasts liquid methane rivers that carve valleys into icy bedrock, while Venus' highland regions show telltale signs of ancient water erosion before its greenhouse effect boiled the planet dry. Even Pluto's frozen surface bears streaks that might be remnants of nitrogen rivers flowing under vastly different climates. The Fink's resilience offers a framework for understanding these alien systems. Its ability to persist through Australia's dramatic shifts from rainforest to desert suggests that even on worlds with extreme climate swings, rivers might survive underground long after their surface flows vanish, a tantalizing hint for places like Mars, where subsurface water could still exist today. The most profound lesson, though, lies in patience. The Fink didn't reveal its secrets quickly. Its story unfolded grain by grain over centuries of study. Similarly, decoding Martian rivers requires matching their sediments to Earth's most enduring waterways, using every tool from isotopic analysis to 3D terrain modeling. When scientists compare the Fink's iron-rich concretions to similar nodules spotted by Mars rovers, or match the Fink's buried clay layers to minerals detected from orbit, they're not just reading rocks, they're translating a universal language of water written across the cosmos. This cosmic perspective transforms how we see our own planet. The Fink's journey from primordial torrent to desert survivor mirrors the broader arc of water in the universe, a fleeting resource in most places, but on rare worlds like Earth, a force that endures just long enough to nurture life. As we continue scanning the stars for river valleys and deltas, the Fink stands as both a guide and a cautionary tale, proof that even the mightiest flows can vanish, but also that their echoes linger, waiting to tell their stories to anyone willing to listen. The Fink River's winding path through Australia's arid heartland wasn't just a lifeline for ancient ecosystems, it was a highway for humanity. For the first Aboriginal peoples who arrived on the continent some 65,000 years ago, rivers like the Fink offered more than water. They provided a roadmap through an unfamiliar land. Archaeologists have uncovered stone tools and ochre pigments along its banks, some dating back tens of thousands of years, clustered in areas where the river's course creates natural corridors between mountain ranges and deserts. These finds suggest the Fink wasn't just a resource, it was a guide, its flow directing seasonal movements and long-term migrations across generations. One of the most revealing sites lies near the river's junction with the Palmer tributary, where excavations uncovered a seasonal camp used repeatedly over millennia. The layers here read like a diary of survival. Fish bones from when the river ran perennial kangaroo teeth marked by stone tools during drier periods, and even seeds from ancient grindstones showing how people adapted their diet as the climate shifted. What's striking is the continuity. The same hearths were reused across centuries, their ash layers stacked like pages in a family history. This wasn't just a campsite. It was a waypoint, a place where knowledge of the river's rhythms passed from elders to children through countless generations. The river's resources shaped more than daily survival. They enabled cultural exchange. Ochre quarries along the Fink's upper reaches supplied vibrant red pigment found in rock art hundreds of miles away, evidence of trade networks that followed waterways like threads. Shells from distant coasts turned up in burials along its banks, carried inland along routes that likely shadowed the river's path. Even the dreaming stories of the errant people reflect this connectivity, with songlines tracing the Fink's course as a spiritual and physical thoroughfare linking sacred sites across the continent. But humans didn't just follow rivers, they transformed them. Along the Fink's middle reaches, centuries-old fish traps still lie hidden beneath the water, their stone walls funneling prey into easy reach during seasonal runs. These structures, some dating back over 7,000 years, are among the world's oldest known aquaculture systems, showing how indigenous Australians engineered the river without disrupting its flow. Elsewhere, fire stick farming, the deliberate use of controlled burns, reshaped the vegetation along the banks, creating open woodlands that attracted game and reduced catastrophic wildfires. These practices weren't just sustainable, they enhanced the river's productivity, turning it into a managed landscape long before the concept of conservation existed. The irony is that modern alterations have been far less harmonious. Since European settlement, groundwater extraction and introduced species like camels have disrupted the Fink's delicate balance, shrinking pools that once persisted through drought. Yet even these changes echo an ancient truth, that rivers and humans are inextricably linked, each shaping the other's destiny. The Fink story reminds us that waterways aren't just resources to exploit, they're partners in survival, their rhythms etched into human history as deeply as they're carved into the land. The Fink River has outlasted ice ages and continental collisions, but its greatest challenge might be the modern world. Climate change looms like no threat before, altering rainfall patterns that have sustained the river for millennia. Recent decades have seen longer droughts between monsoon seasons, leaving stretches of the Fink completely dry for years at a time. Underground aquifers, the river's lifeline during dry spells, are being depleted by increasing demand from agriculture and remote communities. Satellite data reveals disturbing trends: groundwater levels dropping by as much as 3 meters in some areas, while surface temperatures rise faster here than the global average. These changes don't just threaten the river's flow, they risk unraveling ecosystems that took millions of years to establish, from rare desert fish species to ancient gum trees with root systems dating back centuries. Mining operations pose another existential risk. The Fink's watershed sits atop some of Australia's richest mineral deposits, including lithium and rare earth elements crucial for green technology. While remote locations have historically protected the river from large-scale extraction, new roads and drilling technologies are making once inaccessible areas viable for development. In 2022, exploratory drilling near the Fink's headwaters sparked outcry when sediment runoff contaminated a critical waterhole. The incident highlighted a painful irony. The push for renewable energy solutions could inadvertently destroy one of Earth's oldest natural climate records. Traditional owners describe hearing the river's distress in changed bird calls and dwindling fish populations, warning signs that science is only beginning to quantify. Yet hope flows from unexpected sources. Errant rangers have partnered with hydrologists to implement innovative conservation strategies, like strategically placed rock weirs that slow water loss during droughts. Solar-powered sensors now monitor flow rates and water quality in real time, creating an early warning system for ecological shifts. Perhaps most promising is the revival of traditional fire management practices, where controlled burns reduce vegetation that would otherwise consume precious water. These efforts aren't just preserving the river, they're proving that indigenous knowledge and Western science can work together to heal landscapes. The ethical dilemma cuts deep. How do we balance preservation against progress when dealing with a river that holds clues to Earth's very origins? Some argue the Fink's scientific value justifies UNESCO World Heritage status with strict protections, while others emphasize the need for local economic development. What's undeniable is that once lost, this 350-million-year-old chronicle can never be recreated. Every disrupted sediment layer means pages torn from Earth's autobiography. Every dried-up tributary silences a voice that's whispered since before the dinosaurs. This isn't just about saving water in the desert, it's about safeguarding a library where every grain of sand holds stories we've barely begun to read. The Fink's greatest lesson might be its fragility, reminding us that even the mightiest forces of nature need guardians in an age of unprecedented change. The Fink River's 350 million years of survival hold more than just geological secrets. They offer a masterclass in resilience for our modern water crises. Unlike engineered systems that falter under drought or flood, this ancient waterway has adapted to every climate swing Earth has thrown at it, from ice ages to scorching arid spells. Its strategies aren't locked in textbooks, they're written in the way its waters vanish underground during dry periods, only to resurge after rains, or how its floodplains act like sponges, absorbing excess water to release it slowly over years. These aren't quirks of nature, they're blueprints for sustainable water management in an era of climate uncertainty. Take groundwater recharge, a technique now being mimicked from Arizona to Australia. The Fink's natural system of filtering water through porous sandstone into underground reserves has inspired engineers to create managed aquifer recharge projects. In California's Central Valley, for example, drought-stricken farms are flooding fields during wet seasons, allowing water to percolate down and replenish aquifers, a direct echo of the Fink's age-old methods. Similarly, the river's braided channels, which spread water across wide areas to reduce evaporation, are being replicated in places like Namibia, where artificial floodplains now revive parched ecosystems. These innovations prove that the best solutions aren't always high-tech. Sometimes they're written in sediments laid down before humans walked the earth. But the Fink's lessons go beyond hydrology. Its very existence challenges our obsession with permanence in water infrastructure. Modern dams and canals often fight against a river's natural variability, but the Fink thrives by embracing it. Indigenous practices along its banks, like the errant seasonal use of different waterholes, show how human systems can harmonize with this ebb and flow. Today's water managers are starting to listen. In Colorado's drought-prone basins, officials now allocate water rights based on variable flow models inspired by ancient rivers rather than fixed quotas. Even flood prevention is being rethought. Rotterdam's Room for the River program, which gives waterways space to expand during storms, mirrors the Fink's natural floodplain dynamics. Perhaps the most profound shift is recognizing rivers as living archives, not just pipelines. The Fink's sediments contain records of past megadroughts that lasted centuries, warnings about what our future could hold. By studying these layers, scientists have identified patterns that help predict which regions are most vulnerable to aridification. In the American Southwest, tree ring data and ancient river deposits now guide reservoir policies, proving that geologic history isn't just academic, it's a survival tool. This reframes rivers from resources to mentors. The Fink doesn't just quench thirst, it teaches us how to endure. Its channels show how to distribute water equitably across landscapes. Its underground reserves demonstrate long-term storage, and its floods remind us that control is an illusion. In a world racing to desalinate oceans or pump clouds for rain, the humblest solution might be to heed the wisdom of waterways that have outlasted civilizations. The future of water isn't just in new technologies, it's in the old rhythms written in rivers like the Fink, waiting for us to read them. One of the biggest myths about ancient rivers like the Fink is that they must be massive, Nile-sized waterways to have survived so long. In reality, age and size have little to do with one another. The Fink is proof. While it stretches over 400 miles, much of its course is dry for years at a time, reduced to a chain of waterholes in the desert. What makes a river ancient isn't how much water it carries, but how long it's maintained its fundamental connection to the landscape. The Fink's secret lies in its geologic inheritance, a path etched into the continent's bones, allowing it to persist even as lesser rivers vanished. Another misconception is that old rivers stay locked in one course. The Fink's bends tell a different story. Satellite images reveal ghostly traces of past channels sprawled across the desert like discarded ribbons, evidence that even the most enduring rivers dance with the land. Tectonic shifts, climate changes, and erosion constantly reshape their paths, just very slowly by human standards. The Fink's current route might look permanent, but drill into its sediments and you'll find layers recording dozens of abandoned meanders, proving that stability isn't about standing still, but adapting without breaking. Then there's the confusion between geologic age and cultural memory. A river might be ancient in scientific terms, like the Fink's 350 million year lineage, while being young in human experience. The Nile, for instance, is geologically younger but far older in recorded history. This duality matters because it shapes how we study rivers. The Fink's indigenous custodians measure its age not in zircon crystals, but in generations of stories, creating a timeline that complements rather than contradicts scientific dating. Both perspectives reveal truths the other might miss, like how the river's memory of past climates lives not just in rock layers, but in oral traditions describing vanished species and forgotten flood patterns. Perhaps the most persistent myth is that ancient rivers are relics frozen in time. The Fink defies this daily. Its intermittent flow isn't decline, it's a survival strategy perfected over eons. During rare floods, the river transports enough sediment to rebuild entire stretches of its channel overnight, demonstrating a vitality that belies its age. Even its quiet phases pulse with hidden activity as groundwater seeps through porous stone, sustaining roots and replenishing aquifers. This dynamic stability, the ability to shift between torrent and trickle without losing identity, is the hallmark of truly old rivers. Yet for all we've learned, unanswered questions swirl like eddies in the Fink's pools. How much of its original course remains intact from Pangean times? Could its headwaters once have connected to now separated river systems across Gondwana? And most tantalizing, what undiscovered fossils or minerals might lie buried in its unexplored strata? These mysteries remind us that the world's oldest rivers aren't just history books to read their conversations still unfolding, offering new revelations to those who listen closely. Even after centuries of study, the Fink River guards secrets that defy explanation. One of the most puzzling gaps lies in its sedimentary record. There's a mysterious 70 million year span where the river's geological diary goes eerily blank. This isn't just a missing chapter, it's an entire epoch erased, coinciding with the catastrophic asteroid impact that wiped out the dinosaurs. Did the Fink dry up completely during this global chaos, or did its waters churn so violently that they scoured away all traces of their passage? The answer might lie in zircon crystals yet to be analyzed, or in undiscovered sediment layers buried beneath the Simpson Desert. Then there's the riddle of the river's sharpest bends, kinks so abrupt they seem to defy the laws of hydrology. Modern rivers typically curve gradually, shaped by steady erosion. But the Fink's hairpin turns, like the famous Devil's Elbow, follow fractures in the crust that shouldn't exist in this geologically stable region. Some researchers theorize these fractures are scars from a near-miss asteroid strike over 300 million years ago, while others argue they're remnants of a long-vanished subduction zone, a tectonic relic from when Australia was stitched together from smaller continents. The truth might require penetrating radar capable of mapping bedrock 10 miles down. Technology still on the drawing boards. Even the river's origins remain contentious. While most agree the Fink began flowing during the Carboniferous period, its exact birthplace is lost to time. Some sediment traces suggest its headwaters once lay in Antarctica before continental drift tore the landmasses apart. If proven, this would mean the Fink is even older than currently estimated, a river spanning not just geologic ages, but supercontinents. Future advancements in paleotopographic modeling could reconstruct these vanished landscapes, turning speculation into fact. The greatest enigma, though, may be biological. Despite the Fink's extreme aridity, its isolated waterholes harbor species found nowhere else, like the Fink River hardyhead fish. These pockets of life raise a tantalizing question. Could underground tributaries still unmapped be connecting these oases like a secret plumbing system? DNA analysis of aquatic organisms might reveal hidden connections, while next-generation subsurface imaging could expose tunnels carved by ancient floods. What makes these mysteries thrilling is their solvability. The tools to crack them: quantum gravity sensors for deep Earth scans, AI-powered sediment analysis, even microbial DNA clocks are already in development. The Fink isn't done teaching us. Every unsolved puzzle is an invitation, a reminder that the oldest rivers keep their deepest stories hidden until the right moment and the right minds come along to hear them. The Fink River doesn't just flow through the desert, it flows through the dreams of those who have known it longest. For the errant people, its waters are a canvas, its bends a chorus in an unbroken songline stretching back tens of thousands of years. Walk into the art studios of Alice Springs today, and you'll find contemporary Aboriginal painters like Gloria Pangea translating the river's ancient pulse into vibrant acrylic swirls. Her work, Our Water, depicts the Fink not as a static landmark, but as a living entity, its channels branching like veins across the canvas, dotted with symbols for waterholes and ancestral footprints. These paintings aren't just art, they're maps encoding knowledge of seasonal flows and sacred sites in a visual language passed down through generations. Listen closer, and the river sings. Traditional songs performed by errant elders mimic the Fink's rhythms, the staccato beats of raindrops hitting dry riverbeds, the undulating melodies of floodwaters surging through narrow gorges. One ceremonial song, Athara in Keem, River of My Heart, describes the Fink's journey from mountain springs to desert plains, its verses naming plants and animals that signal changing water levels. Scientists have discovered these lyrical observations match modern hydrological data with uncanny precision. When elders sing of the time when the river ran backward, for instance, geologists now suspect it references a long-forgotten tectonic shift that temporarily reversed the Fink's flow, a cataclysm preserved not in rock layers but in melody. This fusion of art and earth science is rewriting how we document environmental change. When researchers compared aerial photos of the Fink's shifting channels with bark paintings from the 1920s, they found Aboriginal artists had recorded meander patterns later erased by floods. The paintings served as accidental archives, capturing details no surveyor's map had noted. Similarly, modern activists are harnessing these cultural narratives to protect the river. Campaigns like Listen to the Fink pair water quality data with oral histories, showing how pollution levels correlate with traditional owners' warnings about sick water from the 1970s. Yet the river's cultural resonance extends beyond its banks. In Australian literature, the Fink appears as both muse and metaphor. From Indigenous writer Alexis Wright's epic Carpentaria, where it symbolizes resistance to colonialism, to modern poetry collections that frame its persistence as a counterpoint to human impermanence. Even its name carries weight. Fink honors a German explorer, but many errant prefer Larapinto, meaning serpent, tying it to the rainbow serpent creation story. This duality, colonial and indigenous, scientific and spiritual, makes the river a mirror for Australia's own identity struggles. What emerges is a truth deeper than any single discipline can contain, that rivers are stories as much as they are waterways. The Fink's endurance isn't just measured in zircon crystals or sediment layers, but in the hands that paint it, the voices that sing it, and the generations who have loved it. To stand by its banks is to stand at the confluence of time and culture, where every ripple carries meanings both ancient and new. Standing by the Fink River, it's easy to feel small, a fleeting visitor to a story written over hundreds of millions of years. But here's the thing, you don't need to travel to the Australian outback to touch deep time. Right now, wherever you are, there's likely a river or stream nearby with its own ancient tale to tell. Maybe it's the gentle creek behind your neighborhood, its banks layered with sediments from the last ice age, or the wide, slow-moving river downtown, its meanders hiding clues to long-vanished glaciers or volcanic eruptions. These waterways aren't just scenery, they're living archives, and with a little curiosity, anyone can learn to read their pages. Start by looking down. Next time you're near a riverbank, notice the colors and textures of the exposed soil. Those stripes of sand, silt, and gravel aren't random, they're chapters in a story. A layer of coarse pebbles might mark a prehistoric flood, while fine, dark soil could be the remnants of a forgotten forest. If you're lucky enough to spot rounded stones, try imagining the currents that smoothed them over centuries. Even the shape of the valley holds secrets. Steep, V-cut gorges often point to young, energetic rivers, while wide, lazy bends suggest an older waterway that's had time to wander. For a hands-on experiment, fill a clear jar with water and scoop in a handful of river sediment. After it settles, you'll see layers form, a miniature stratigraphy lesson in your kitchen. The heaviest grains sink first, replicating how rivers sort minerals over geologic time. Those tiny particles might contain zircon crystals older than the dinosaurs, or flecks of mica from mountains that eroded millennia ago. It's a reminder that every river, no matter how modest, is a conveyor belt for Earth's history, carrying fragments of the distant past to our present. But the real magic happens when you connect these observations to your local landscape. That hill your town is built on, it might be the remnant of an ancient river terrace left behind as the water carved downward. The flat fields nearby could be floodplain deposits, laid down over thousands of years of seasonal overflows. Even urban rivers, now channelized between concrete walls, often follow paths etched during the last ice age, their courses dictated by long-vanished ice sheets or meltwater torrents. This isn't just about geology, it's about perspective. When you start seeing rivers as timekeepers, the familiar becomes extraordinary, the cobblestone used in your city's historic district. Likely quarried from an ancient riverbed, the clay in your pottery class, once mud on some forgotten floodplain. Water shapes not just the land, but the materials we build our lives with. And by paying attention, we join a lineage of observers from indigenous elders to early naturalists who have understood that rivers are more than water. Their memory carved in stone, so the next time you cross a bridge or skip stones by a stream, pause for a moment. That water flowing past has traveled unimaginable distances, not just through space, but through time. It's carried molecules that once swirled in primordial oceans, weathered rocks from vanished mountains, and nourished life in forms we'll never know. The Fink's epic saga isn't unique, it's just one verse in a planetary poem written by rivers everywhere, and your local waterway, however humble, holds verses of its own. All you have to do is look. The Fink River's waters have carried more than just sand and stone, they've carried the weight of Earth's epic story, from the violent birth of continents to the quiet moment life first took root on land. Its currents are a thread connecting us to a time when mountains rose like titans and plants were just beginning their march onto dry ground. But this river isn't merely a relic of the past, it's a living testament to the forces that continue to shape our world. Every twist in its course, every layer of sediment, every fossil hidden in its banks is a reminder that rivers don't just flow through history, they write it. Think about what this ancient waterway has witnessed. Its waters have mirrored the breakup of supercontinents, the rise and fall of species, the slow dance of climate change across hundreds of millions of years. When we study the Fink, we're not just looking at a river, we're seeing the blueprint of our planet's evolution, those ripple marks preserved in its sandstone. They're echoes of currents that flowed before dinosaurs walked the earth. The iron-rich bands in its cliffs, they tell of an atmosphere so alien it would choke us in seconds. Even its dry stretches whisper secrets, holding groundwater that survived ice ages and scorching droughts. Yet the Fink's greatest lesson might be its fragility. For all its resilience, this river, and others like it, now face threats no geologic era could have prepared them for. Groundwater pumping, climate shifts, and human encroachment are erasing pages from Earth's archive faster than we can read them. Protecting these waterways isn't just about conservation. It's about preserving the very libraries of our planet's past. Imagine losing volumes of a novel we've only just begun to decipher. That's what's at stake when ancient rivers are altered or destroyed. But there's hope. From indigenous-led conservation efforts to cutting-edge research, people are fighting to keep these liquid time capsules flowing. Every waterhole restored, every sediment core analyzed, Every traditional story recorded adds another layer to humanity's understanding of our home. The Fink reminds us that rivers are more than resources, they're teachers, chroniclers, and collaborators in Earth's grand narrative. So as we leave the Fink's banks behind, let's carry its lessons forward. Look at the rivers near you with new eyes, whether it's a trickling creek or a mighty waterway. Each one holds fragments of deep time waiting to be discovered. And who knows, maybe the next great revelation about our planet's past or its future lies hidden in their currents. Thank you for joining this journey through the ages. Now it's your turn. Have you ever stumbled upon a piece of geologic history in your own backyard? Share your stories below, and let's keep the conversation flowing. After all, the Fink story isn't over yet, and neither is